Hi everyone, and welcome back to lecture 3 of the course Machine Learning 1. My name is Deepak Gupta and I'm an adjunct professor at TechSmin Hub, IIT Dhanbad. And this course is a part of the skill development program sponsored by TechSmin Hub together with the help from Transmute AI. Today we will first start with understanding what is expectation, what is variance, and what is covariance. So expectation. In simple terms, expectation can be defined as an average outcome of an experiment. So it is an average of some function under a certain probability distribution. We have seen random variables, we have seen probability distribution. If we are given a probability distribution for a certain random variable, and if we are taking the average over that distribution for a certain range in case of certain range, so in an average sense, what can be the possible value of the random variable? That is referred to as expectation. So it can be defined for discrete variables as well as it can be defined for continuous variables. So let's try to understand what expectation is first for discrete variables. So if we look at here, there is a random variable x that can hold values 0, 1 and 2, and the probabilities for these different values: for 0 it is 0.16, for 1 it is 0.48, and for 2 it is 0.36. Now we define expectation over f. So expectation for this random variable, it can be defined as summation over x, so summation over all possible all possible values of the random variable, px multiplied by fx. So in this case it would just be 0 into 0.16 plus 1 into 0.48 plus 2 into 0.36, and the expectation is then the summation of these three terms. So this is how expectation is defined for a discrete random variable. And when we see what it is really, so the expectation, so the random variable can have values 0, 1 and 2, right? Now the expectation is an average value that we assign to this random variable. That's how it can be interpreted. How do we so let me put it down. Yeah, okay. So how do we define it for continuous variables? So for continuous variables, this summation changes into an integration. So we have integral of px multiplied by fx then dx, and this in this case this for example, I mean this is not really consistent with this. So let's try to understand here. So we have the probabilities defined. So this fx is the probability distribution, probability density function, that in case of continuous random variables we have this probability density function. So this fx, and then this is the value of the random variable. So we multiply 1 over 60 x cube into x, and then we take an integral from minus infinity to infinity, and then we just simplify the integration and we end up with 3.33. So that is the expected value of this continuous random variable. So we see here that the random variable could hold values from 2 to 4. And if I mean, if in a simple sense, if you let's try to understand in a simple sense that if this was just, if all values would have had same probability, if it was a uniform distribution, then the average value would be somewhere in the midpoint, which would be 3. But since we have this probability density function, when we take out the expectation, we end up with 3.3. So this is the procedure of how we compute the expectation for a continuous random variable. Now the other term is variance. What variance gives you? So first, from the expectation we got an average value that a random variable can hold. Now variance, it gives you an estimate of the spread, how far your observations are spread out from your average value. And how do we mathematically define it? It is, the variance is defined as the expectation of each value minus the expectation and then a whole square. So this is how we define variance. And now then let's try to simplify this. This expectation, we can just open this whole square inside, and then we have expectation of fx square minus 2fx into expectation of fx plus expectation of f of x whole square. Now from the scaling property, we have this. that the expectation of a constant term multiplied with a fx can be written as summation c. So the expectation of fx is summation fx px, and when the function is multiplied with c, we put the c inside, and then since the summation does not change with respect to this constant, we just take out the constant outside and then again turn it into an expectation, so it can be written as c times expectation of fx. So this scaling property holds. Based on this, what we can write here, we can write it as expectation of f of x whole square minus 2 times expectation of f of x square. So how does this come in? So we have this whole thing inside the expectation, right? So we have expectation of 2fx, expectation of fx. Expectation of fx is a constant. So we take it outside of this expectation, and then we have expectation of fx, this expectation of fx multiplied by expectation of 2fx. We can take 2 also outside, so we get minus 2 into expectation of fx into expectation of fx. And then the last term is just the expectation of f of x whole square. I mean, this one doesn't change, right? Expectation of expectation, it is not going to make a difference. So that brings us to expectation of fx square minus, this cancels one of these, minus expectation of f of x whole square. So the variance, what we see here, the variance is just expectation of the f of x square minus expectation of f of x whole square. We will use this property a lot in our later lectures, so try to remember this. Now, the third term is covariance. What covariance gives is, if we have two random variables, it gives an extent to which two variables vary together. So if we have a random variable x, if we have a random variable y, the covariance gives you an estimate of how much does y change when x changes. If both are completely independent from each other, then the covariance is 0. So the covariance gives you an estimate of how two variables vary together. Now, mathematically, we define covariance as, so if we have random variable x and random variable y, then the covariance xy can be defined, can be defined as expectation of xy, where xy in the joint probability distribution x comma y, it is defined as x minus expectation of x into y minus expectation of y. So before I go further in simplifying this, let me show you this. So when in the covariance equation, if x and y are the same random variable, then it turns into variance, and this can also be validated. So if we put y is equal to x, we end up with x minus expectation of x whole square. So now in this case, this is covariance. So we have this. Now if we multiply the two terms and expand further, we have, if we are expanding this whole term, we have expectation of x times y minus expectation of minus, we have x times expectation of y. We have an expectation outside, right? And then we have minus y times expectation of x plus expectation of x expectation of y, and then we split these four terms, and we get expectation of xy, and then from here we have expectation of x expectation of y with a negative sign. From here we have expectation of y, and then this whole term goes outside, so expectation of y into expectation of x with again a negative sign, and then expectation of this whole thing is again the same thing, so we have one expectation of x into expectation of y with a positive sign. So we end up with a single expectation x expectation y with a negative sign. So the covariance of xy is now expectation of xy minus expectation of x expectation of y. And again, if we put x is equal to y here, we end up with expectation of x square minus expectation of x whole square. That's what we also saw in the previous slide. So this is how we compute covariance. Now, here we assumed x and y to be scalars. What if they are not? What if they are vectors? By vector, if you recall from our first lecture, we defined vector as every random variable being expressed with multiple values. So with, let's say, three values defining one random variable, so it will become a vector. How we denote covariance in terms of vectors? So covariance of x comma y is, where these bold notations are vectors, is x minus expectation of x into y minus expectation of y transpose. This transpose is there because then you can make a element wise multiplication. That's why we have this transpose here. And then if we again do some multiplications, we end up with x times y. So this one we can expand, and we simplify this, we end up with expectation of xy transpose minus expectation of x into expectation of y transpose. So that's how we compute the covariance between two vectors x and y. The expectation, the variance, and this covariance we are going to rigorously use in our later lectures when we look into more details about the probability distributions themselves. Thank you.